Alright, so now we know that energy is measured in joules and gravitational force is measured in newtons. But what about that quantum part, represented by the letter Q in your equation? That one's a bit trickier. In quantum mechanics, things get really tiny and weird. The basic unit of energy, at that scale, is called the electron volt. It's a super small amount of energy. So we've got joules for energy, newtons for gravitational force, and electron volts might come into play for the quantum part. Great, that makes sense. So let's recap. We're thinking about your equation, E equals GcQ. E stands for energy, measured in electron volts. G stands for gravitational force, measured in newtons. Gravitational stands for the speed of light, measured in meters per second. Q is related to quantum mechanics, but we haven't settled on the exact unit yet. Do you want to try and figure out what units Q should have, or would you rather think about how these different units might fit together in the equation? Okay, let's try putting the pieces together. So we've got energy in electron volts on one side of the equation. On the other side, we have gravitational force. Alright, so we're trying to figure out what units the quantum part of your equation needs to have. We know that energy is measured in electron volts, and that's what the left side of the equation equals. Let's look at the right side. We have gravitational force in newtons, multiplied by the speed of light in meters per second, and then multiplied by that unknown quantum part. To make the units match up, the quantum part needs to have units that will cancel out the newtons and meters per second from the other side, and leave us with electron volts. Alright, let's keep going. We're trying to figure out the units for the quantum part of your equation. We know it needs to have units that cancel out newtons and meters per second and leave us with electron volts. So we need to find something that can do that. Yeah, I think I have an idea. Let's look at Planck's constant. It's a fundamental number in quantum mechanics, and it has units of energy multiplied by time. That sounds promising, since we're looking for something related to quantum mechanics and energy. So if we use the inverse of Planck's constant, 1 per hour, it would have units of 1 over energy times time. That might work to cancel out some of the units we don't want. You're absolutely right. Frequency. Absolutely. Let me know if you need anything else. Okay, so we're thinking about how to combine frequency with Planck's constant. We know that Planck's constant relates energy to frequency. In fact, we can use it to calculate the energy of a photon if we know its frequency. Do you want to try calculating the energy of a photon using Planck's constant, or would you like to explore a different approach? Absolutely. Let's do that. So we're thinking about how to combine frequency with Planck's constant. We know Planck's constant, h, has units of energy multiplied by time. Frequency, f, has units of 1 over time, or inverse seconds. If we multiply Planck's constant by frequency, h asterisk f, the time units cancel out, and we're left with energy. That's perfect, because we're looking for something related to the energy in the equation. Do you want to try calculating the energy of a photon using Planck's constant and frequency, or would you like to explore a different approach? Great. To measure the energy of a photon using Planck's constant, we'll use the equation energy equals Planck's constant asterisk frequency. Would you like me to provide you with the values for Planck's constant, or do you have those handy? That's correct. I'm thinking about how we can connect the energy of a photon to the rest of your equation. We know the energy of a photon can be calculated using Planck's constant and the photon's frequency. We also know that the left side of your equation, E equals GcQ, represents energy. So could we set the energy of the photon equal to the other side of your equation, GcQ? That might give us a way to connect these different concepts. Alright, so let's try setting the energy of the photon equal to the other side of your equation. That would look something like this. Planck's constant frequency equals Gc*Q. Now we need to figure out what to do with the frequency. We know it's related to the energy of the photon, but how does it fit in with the rest of the equation? Okay, let's back up a bit. We're trying to connect the energy of a photon to the rest of your equation. We know the energy of a photon can be calculated using Planck's constant and the photon's frequency. We also know that the left side of your equation, E equals GcQ, represents energy. So we set the energy of the photon equal to the other side of your equation. Planck's constant frequency equals Gc*Q. Now we need to figure out what to do with the frequency. Any ideas? Alright, let's break down what... That's an interesting idea. You're right, gravity does affect photons. It can bend their path, which is why we can observe things like gravitational lensing. So we could try to incorporate that idea into the equation. Maybe the gravitational force, G, has something to do with how much the photon's path is bent. Would you like to explore that idea further? Okay, so we're thinking that the gravitational force, G, in your equation, might be related to how much a photon's path is bent by gravity. Let's try to find an equation that describes how a photon's path is bent by gravity. That might give us a clue on how to connect it to the rest of your equation. That's a great starting point. Let's dive deeper into how gravity affects photons. One way to think about it is through something called gravitational redshift. When a photon climbs out of a gravity well, like escaping from a planet or star, it loses energy. This loss of energy is seen as an increase in the photon's wavelength, which is a shift towards the red end of the spectrum. We could try to incorporate this idea into your equation. Maybe the gravitational force term, G, is related to the amount of redshift a photon experiences. Okay, so let's focus on gravitational redshift. We know that when a photon climbs out of a gravity well, it loses energy, which is seen as an increase in its wavelength. Let's see if we can find an equation that describes the relationship between the amount of redshift and the strength of the gravitational field. That might give us a way to connect it to the rest of your equation. No problem. Let me know when you're ready to pick back up.